Hours for this class on a weekly basis, sometimes twice a week, as allowed by my schedule, and that will include Thursday and maybe Friday as well. Okay, for those who are working on problems that's late, etc., and for projects. I know a variety of you are making good forward progress on projects. I'm actually really excited about the projects that several are working on. I think there's some neat stuff being done, and so I'll do what I can to make sure that you get your support to wrap them up prior to that deadline, which we set, I think, just about 4 days before the final. Today, I wanted to talk about topics that we weren't able to cover in this class. In general, I'm fairly pleased with how this class has gone for a first time run of a more abundant class. And I'm impressed by some of the material that you folks have been able to absorb. However, there's a variety of topics that we haven't been able to address. Some of these are more prosaic. They have to do, for example, with AnyLogic capabilities that are well covered in some of my other lectures you'll find online. And some of these things, I'm mentioning in part because some of these things may be useful to those doing projects. For example, there's coverage of data collection in AnyLogic. How do you actually collect data in these things called data sets and output it? You've acquainted yourself with data sets, I think, for the final problem set, but there's more you can do with them. Debugging. I show how you can attach an external debugger, for example, Eclipse debugger, to AnyLogic models and debug them line by line. It turns out that AnyLogic's Professional Edition actually comes with the debugger that works at a higher level. For example, you can set breakpoints on transitions, on events, and proceed appropriately. So it affords a higher level of debugging. But frankly speaking, I agree with, I think it was Ken Thompson and maybe Hugh, some of the inventors of Unix, who commented in one of their books, commenting on programming style, that debugging tools can be valuable, but typically the most valuable part of a debugging session, almost always, is really about the situation. And you can do amazing debugging with the smallest of resources. So I've spent a fair bit of time in hardware labs, debugging hardware. And I would use, for example, LED blinks as indications of what's going on. I would deliberately make the hardware crash in a noticeable way if a condition was being violated. You can, if you're consistent in your thinking, careful in your experimentation, and reflective of sort of hypotheses you're trying to advance, you can be very effective at debugging with minimal resources. So while there are debugging tools, a lot of what comes into being effective at model debugging is really thinking carefully about what's going on in the model, putting in artfully chosen markers of one sort or another. It could be as simple as print statements to indicate when some certain actions of relevance are occurring, and you can zero in on what's going on. There's a whole art to debugging. For a couple of years now, I've been working towards compiling a really nice lecture on debugging. You'll find in this other set of materials a sort of pale cipher of it, but it has what may be some useful comments on debugging methodology in AnyLogic. There's another set of lectures I have online, which are hierarchical models. They involve models which involve multiple levels of hierarchy, say person, city, region, and stuff like that, and show how those can be constructed. Diverse sorts of hybrid models, system dynamics models within agents, agents within system dynamics models, agents within discrete event models. You can have discrete event models within agents. All sorts of different interesting combinations are quite seamlessly supported within AnyLogic. And some of my other lectures highlight some examples of those. And this is not merely a convenience, it's not merely a hack. It turns out there's certain formalisms that have been put forward, what are called hybrid automata, which are hybrids between discrete phenomena on the one hand and continuous phenomena on the other. So you go and you're in a set of states, and in each set of states a set of differential equations apply, for example. And then you transition to a different set of states where a different set of differential equations apply. And AnyLogic's hybrid modeling can support fairly rich sort of artifacts such as that. Building up user interface in AnyLogic, this is not something we've talked about. Based on your background, I didn't think we needed a whole lecture on adding widgets to your model, either at the level of main or the level of experiments, or even at the level of person, adding radio buttons and adding drop downs and adding, buttons that you push and interesting things happen. You folks are mature enough that I didn't think that would be the best use of time. But you should know that it's really easy to do. About as easy as you expect. Throw it in, write some event handlers, you're off to the races. So, there's lectures on that where I do talk about that in more detail. And one thing you do want to be very clear about is, if you put those things in an experiment, they can help you set the initial conditions for the model, which when you then initiate it, it runs with those initial conditions. If you put those in main, those are throbbing model parameters or model variables all through the model while it's running. So if you have a slider in the experiment, often that's just associated with setting up the model to run. Fires up the model, its job is done. If you're putting it in main, you can slide that slider and watch as the behavior change, right? That makes sense. One's living in a kickoff place for the experiment, one's living in the actual main class itself. And finally, there's some lectures on performance and computational burden. Those of you doing projects might find some of this of interest. So for example, I talk about how to spot possible components of the model that are chewing up a lot of cycles, and how to lower that performance burden. For example, by creating versions of your model that use no visualization as well as those that do have it. You don't have to change the underlying model. You just use a different sort of experiment. For example, parameter variation experiment calls a model's run fast method, which runs it without visualization, whereas a normal type of experiment, a scenario type of experiment, runs it with visualization. And that visualization can have a big burden on performance, impose a big burden on performance. So there's a lecture where I talk about that, and I think it should be pretty straightforward to you folks. One of the key principles is this is an event-driven system. More events, slower it will go. If you can cut down the number of events firing, faster your model will go. Okay, so those are some topics I consider more prosaic. Let's talk about topics that are a little bit deeper in their significance. I'm going to fly through. Sophie can put together some more slides for this, but I've been caught up with other classes and burning tips and so on. I was going to talk about a set of topics that might give you glimpses as to further horizons within the modeling world. And I have assembled a bunch of slides, and I'll probably talk in addition to that. So one thing is this issue of linking dynamic simulation models with statistical tools. This is a topic that Seth is getting into a little bit in some of his project work. But we'll talk about two ways of bringing these things together. What we're seeing right now is quite unprecedented in my 20 or so years of experience working with these models, between 20 and 25. We're seeing sort of a confluence of the world of computational statistics on the one hand and simulation modeling. And it's really interesting because the conceptual frameworks are quite different. The formalisms are different. the conventions of what constitutes evidence and so on are different. But the two are, I was going to say in a crash course, but that makes it sound more transgressive than it is. They're coming together in a very powerful sort of ways. And we'll talk about two ways that these things come together. One of them is so-called predictor-corrector models, which have to do with linking models and data. Okay? And secondly, we'll talk about use of Markov chain Monte Carlo techniques and sequential Monte Carlo techniques in the context of predictor-corrector, which are techniques formally rooted in often in Bayesian statistics, but which seek to, for example, sample from distributions which might be derived from the underlying simulation model. So we'll talk about how these two are coming together in some interesting ways and some of the formalisms involved there. Another topic is this issue of linking models and data. And I think of all the people here, maybe only Alex has seen a glimpse of this. So one of the big, if we talk about several trends, one is this merging of statistical simulation, computational statistics coming together with dynamic modeling. Another one is the rise of dynamic modeling for decision-making in diverse areas, which is really taking some areas by storm, health being one of them where it's most active right now. But another big trend is the trend toward what's called big data. So when I was a young man, and in your shoes, the world was a different place. It was a lot more siloed, a lot more divided into sort of solitudes associated with different disciplines, and there was a lot more resistance to cross-disciplinary work. But another side of it was that often data was incredibly hard to come by. And so if you went to biologists, for example, my wife's a biochemist, MD, PhD, and she was working before MD in a biochemistry lab. And they would do the most intricate of experiments to collect some data. It was in biology there, the emphasis was in very, very small amounts of data collected with incredible precision and care in a fashion that was often involved fairly small numbers, but great care. And these days, the world of biology and biochemistry is just radically different because of the rise of gene array chips, for example, sequencing machines that can pump out sequence analysis on DNA, do protein sequencing. There's a huge explosion of data related to genomics, related to proteomics. There's data related to pathways that are active within a cell in driving metabolism. So they have these gene expression chips which measure, for example, expression of proteins within a cell. And there's huge amounts of data. Now, the data is not nearly as high quality as some people would like, but one of the things that bioinformatics has demonstrated in a very compelling way is just how much insight you can get from massive quantities of data that is of decent quality, not always sterling, with a variety of cleverly chosen models. And some of those models, ladies and gentlemen, are dynamic models. Not all. A lot of statistical models, machine learning models. But a fair number are models involving simulation. And I've been working in the area of health, big data and health. What's increasingly being known as big data. The creation of the collection of electronically sourced data, increasingly getting too big to store comfortably in relational databases, for example. It may involve the sort of data infrastructure Google uses with big tables out there in the cloud. And this data is increasingly available surprisingly cheaply. It comes from point of sale. It comes from environmental sensors, the sort of sensors that are sprinkled throughout this building. Our buildings are becoming robots, and we can collect data streams from them. We have data easily collected from consumer electronic devices like smartphones or cars, or the electronics in cars, and data from social media, for example, by mining Facebook or by mining Twitter, looking at sort of discussions, etc. And this explosion of data is nothing but numbers if we don't have models to make sense of it. The issue is not the data. The issue is predominantly how do we build models that give us insights from this data? How do we build models that make sense of the data? For example, that link it up to choices to be made, that have to be made. And these days, I'm sort of straddling these two worlds. We've created a system here. It's frankly, I think it's the leading epidemiological data collection system in the world for big data, sensor-based data in health. And we're combining it with a variety of models. These include Bayesian inferencing models, but at its core is dynamic models. Some of the dynamic models are between local individuals, some are within an individual. Blood glucose metabolism, for example, body weight change over time. So this whole issue of bringing together models and data is going to be a big part. If you stay involved with any sort of modeling, you're going to see this coming to the fore in many different areas of the modeling space. How do we make sense of this data? How do we leverage it in our models? And unfortunately, there's big opportunities. Multi-scale modeling, how do we have models that span scales? Models where we have individuals circulating in communities, maybe in neighborhoods, and then individuals, and then within individuals, rich dynamics associated with physiology, for example, with infection over time in the response to the immune system. We do quite a bit of work with that, and it's a early trend, but one that's growing quite quickly. Real-time predictive simulation. How do you do prediction sort of in real time, anticipating where you're going to be in the near future in a way that can inform decisions now? For example, with diabetics, they often look for blood sugar that goes out of range. Right? Their effective body can be damaged, their heart can be damaged, their vasculature, their arteries and veins can be damaged by blood sugar that's out of line. It's out of its normal ranges. And yeah, it's a very crude measure. It's like right now, often the person won't respond until it's out of the range, and then it takes a while for the body to get back in the range. If you could predictively anticipate based on their exercise patterns they've been engaging in, based on the meal they've just eaten, based on hormonal changes, based on level of physical activity in terms of sedentary behavior, sitting, standing. If you could anticipate 15 minutes from now, what will it be? 30 minutes. That could be life-saving in some cases. It can prevent blackout for someone who's hypoglycemic, goes too low. It could prevent long-term damage from someone who has blood sugars that are in the too high region. So predictive simulation in real time is increasingly being used. And so I work with a company in the States, A-Frame Technologies, that leverages alerting systems, for example, to alert people to impending danger, and models can be very useful for that. Model specification in domain-specific languages. Another hat I wear is I have a background in language implementation, computer language implementation, parsing and creating language tools. And one of the things we see is the emergence of frameworks like AnyLogic and much earlier Vensim coming about in the 90s, which make use of graphical languages. And this is not merely a matter of eye candy. It turns out that sometimes by allowing you to draw out a state chart, or drawing out a stock and flow diagram, drawing out events, often what you allow is a modeler to focus on the underlying domain of interest rather than on software engineering. I'm a software engineer too, by training. I teach software engineering, but when I'm thinking about a model and conceptualizing it, I prefer not to be surrounded constantly by variable declarations and software engineering concerns. I prefer to be able to focus on the area. And what we're seeing is languages coming out, whether it's AnyLogic's discrete event modeling toolkit, where you have move to and send to and attach and seize and so on, or whether it's state charts or stocks and flows, we're seeing these languages coming out for characterizing declaratively some underlying system. It's incomplete. We end up filling in a lot of code into it. But increasingly, people are recognizing the value of crafting languages that allow us to express things concisely and clearly with respect to these areas. And I think there's a lot of opportunities to leverage the growth of what are called domain-specific languages. Can anyone give me an example of a domain-specific language that you may have used? Besides Vensim and various languages in any line. In other classes. SQL is a great one. Yeah, it's a domain-specific language up to a database. How about another one? Anyone use XSLT? No? Okay. Innocent of that. Ever used Excel, formulas in Excel? It's a domain-specific language. Did anyone ever draw out circuits in circuit creation packages using a domain-specific language there? You may not think of these as languages. Shockingly, many of them are computationally universal. You wouldn't want to simulate a Turing machine, perhaps. Simulating a Turing machine in XSLT would be sort of akin to maybe writing a video game in Fortran or something like that, or an AI program in Fortran. It would be an exercise in sort of in frustration, perhaps, but it could succeed. So domain-specific languages, crafting languages that support modeling is a really interesting area. Mathematical analysis tools, we just got into some very starting comments on that. How do you determine stability of an equilibrium? How do you find the locations of equilibrium? Eigenvalues and based analysis. It turns out there's a variety of other tools that allow you to analyze models. There's results like the Poincare-Dixon theorem, which show results for global asymptotic stability of a system. And there's some really neat things you can do with a system of ordinary differential equations, for example. Numerical analysis. How many people here have taken Ray Spitatori's numerical analysis course? Okay, so you're familiar that there's a whole depth of issues when it comes to understanding the stability, for example, of a numerical stability of differential equations. Particularly come to the fore with PDEs, partial differential equations. But ODEs can also raise challenges sometimes. You can have stiff ODE systems where we are not terribly interested in characterizing it. This system of stocks and flows, for example, on a minute-by-minute basis. We're more interested on a week-by-week basis. But to have it be correct, to have it be numerically stable, to have it be to yield results that are accurate, we need to simulate it at this finite-grained level. So there's numerical analysis issues. Alternative mathematical formalisms, hybrid automata I just mentioned earlier, differential equations, differential algebraic equations. Turns out that we've taken a look at differential equations, ODEs, which are kind of the granddaddy of continuous formulations, but there's a set of other formalisms that are really neat. And you'll find people using impulse differential equations, stochastic differential equations, for example, hybrid automata for all sorts of different things. And I would love to be able to talk about this. Performance issues. Turns out that one of the big issues here is being able to take advantage of concurrency and parallelism. How many people in here in this class have taken a course in concurrency in computer science? Nadeem Jamali's class? No one? Okay. Well, yeah. Yeah, it's a very interesting class, and in general, the performance of these models, you may have encountered it. There's a lot of embarrassing parallelism, what's called embarrassingly parallel operations. Can anyone give an example of something I say is embarrassingly parallel? It would be like really, really easy to run things concurrently at the same time. Okay, matrix multiplication can be used. There's certainly some parallelism that can be exploited there. But I'm talking about things we've discussed in class or you've done a lot of in class. So that's actually a great example. There's some neat things you can do with matrix multiplication. I don't want to minimize that. But in class, we've seen some things that are embarrassing to parallel. Monte Carlo. Yeah. You could farm out Monte Carlo simulations to 100 different machines, and they could run in parallel. You could load balance them, send out new computations. When it finishes the old one, give it a new one. That's completely straightforward. And there's some aspects of sensitivity analysis and calibration which you might be able to do that for as well to get a more thorough coverage. But then there's other things too. For example, and there's some algorithms like swarm-based algorithms that can take advantage of parallelism in a pretty neat way to get, again, large coverage. But then there's some things that are less obvious, but probably can be decomposed in a fashion that would allow you to exert parallelism. For example, if you have a network of agents, you might be able to divide up the space of agents so that parts of the network with low, are simulated in one place. Maybe there are different components of a network with low cut number between them. In other words, there's few connections that go between them. Why do we want few connections between those areas? So suppose we have this component over here and that component over there. Why is it we want few connections? What do the connections force us to do? So we have these agents here, and these are all tightly connected in some sort of way, and we have another set of agents, maybe it's a different community over here, and we have only a few connections between them. Why does it matter sort of how we chunk them up? Why not just chunk them right down the middle?
Connections imply lower
Dependencies. Precisely. It's neater division without dependencies. Dependencies kill you. And ladies and gentlemen, you could take the man out of language design, but you can't take language design out of the man. Comes back to this in many ways. If we could choose the right languages, often we can parallelize things at this level much more easily, like decomposing things. So for those of you who have taken Chris Duchin's class 340, okay, a couple people. So turns out some of the languages discussed in the class, languages like Haskell, can be mapped more easily to cell processors, where you have large amounts of computation that can go on in parallel. And you can map a situation where you have these sort of agents more readily, more straightforwardly, because the dependencies in those languages, ladies and gentlemen, are more clear. They're more transparent. There's this equational reasoning you can use with them. You see what depends on what much more directly than you do in a language like Java. And as a result, you can map it to parallel hardware much more readily. Another whole area is really interesting, is evaluation of procedures and sort of operations, study design, statistics, using synthetic population experiments. My colleagues over in math call these simulation experiments, but they're using the term in the sense of statistical simulation often. But the idea is that if we have, say, an agent-based model which simulates an underlying population, suppose we have some statistic, we want to test several test statistics for deducing some underlying quantities in the model. We can test those using this model if we know the actual underlying situation. We can test how well they measure some underlying actual property. And these things are really easy to do with models. And planning experiments using modeling. A growing number of people in biology labs, a growing number of people who are planning experiments involving human health or animal health end up planning experiments informed by modeling. It lets them choose more judiciously what to vary, how to vary it, what size of population to measure it from, etc. And here modeling becomes part of the learning process day to day. Okay. So these are some topics that I wish I had time to cover in this course. Looks to me like 494 or something like that. Yeah, more of any version.
If you have a list of recommended books that cover these topics, that would be really appreciated.
Sure.
Because I know you've name dropped a lot of books over the term.
Yes, and I do have some list of books later in here. So great, and I'll see if I can come back to this. I'd like to talk about some of these things though, which I think will, in a more concrete basis, which may open your eye with respect to some opportunities. One is this issue of predictive corrective. If I just one more lecture more lectures, I might be able to fit this in. It's a really neat idea, and it gets this issue of linking models and data. Really, that should be read as well. It also will also see this case of sort of evaluating approaches using synthetic experiment processes. So the idea here is to move beyond open loop models, to have closed loop models which try to predict forward, but use ongoing sources of data along the way to correct themselves, to inform their best guesses. Not viewing that data as perfect, in fact, viewing the data as error prone as well, but using it to sort of cross-check model production. And the example I used one or two times during the course already, and is I think a fairly good one, although it's imperfect as a metaphor. And that is, you have a very good mental model for your at home. But if you try to do it with your eyes closed, you'd be in trouble. You depend all along the way on observation and correction. Maybe an excellent model, maybe a superb model, but you need that ongoing sort of cross-checks. When you're walking, too far off to the side of the corridor, so you don't bump into a pillar. When you're, if you're driving, so your car doesn't go off the road, so that you get on the bus where it actually pulls up at Place Real instead of where it, has on other days. So the idea here is to create closed loop models. Models that, in some sense, observe and learn over time. They learn from observation. So there's a bunch of benefits here in terms of both making sense of the data and benefits of the model. So perhaps most critically for this audience, it prevents the model state from diverging from the actual situation. Our models, I argued early on in this class, all models are wrong, some models are useful. That was done, a quote from George Box, a famous statistician. And okay, don't tell me, are there time? Yes, there are timings in here. I don't know where those came from. So our models are inevitably incomplete. They inevitably omit certain things that are relevant to the world and are important to the world. And as such, if we simulate going forward, even if we aspire to really ground them richly through calibration, parameterization, cross-checking, cross-validation and so on, even if we ground them really, really well on actual data and expert understanding, they're going to divert. We run them forward, they're going to miss the mark at some point. And if we have data, and we can correct these models over time, we can maintain the model freshness. We just reground it in updated data. We can use its prediction going forward as a good best guess, but when new data comes in, we update our understanding. The model learns. This gives us a better understanding of the current situation. We're going to be meshing our best guess from the model with our best guess from data. Neither is perfect. A lot of the time the data has errors in it. So GPS data, for example, if you've never worked with it, it's incredibly noisy. I could show you videos of it, but there's a lot of scattering around your actual location and so on, due to atmospheric effects, etc. And here you can get both model prediction and imperfect data and get something that's better than some parts, greater than some parts. Okay. And for the data, we can understand the implications of the data. We're just measuring maybe one or two things in the model using the data and grounding those things. And the model can make sense of that data for other things in the model or which we don't have observation. Maybe we can't have observation. Can help us understand the implications of that data for decision making, help us separate signal from noise. So how many people here have used GPS devices before? Maybe in iPhones, maybe in Garmin GPS in your car, I don't know what. But, sorry? Yeah, geocaching. So you folks may or may not know it, but actually that has a movement model in it. It actually smooths out the data. In fact, it's gonna have the type we're gonna discuss next. It's something called Kalman filter. It projects forward where you're going, guessing where you're gonna be, and it then gets data from the satellite, but it doesn't automatically assume the satellite data is correct. It tempers its understanding from the satellite data with where you've been recently. And why does it do that? Because the satellite data has an unsettling proclivity towards error. Among other things, sort of has you bopping all around, and sometimes it places you in the most unlikely of places, namely off the coast of Equatorial Guinea in Africa, which is the 0 location for GPS. And Alex, you may have noticed that in some of the presentations in the Geo Crowdsource. Suddenly they're teleported for a single GPS location. People are teleported off the coast of Africa. Another one is just exactly across the world from Saskatoon, which is somewhere in Indonesia. It will suddenly appear there, and then pop back.
Is that also related to the problem they were having where they thought the geosourcing was reporting them being within the Saskatchewan River if they were on the west side? So is that a different issue?
I'm not sure about that. I was puzzled by that. I'm not positive. I was puzzled by that discussion. Here, let's talk about these. So predictor corrector models. We can do this in two ways. The brute force way. You can imagine every time new data comes in. Imagine you have a great model of H1N1 here in Saskatchewan, and I'm lucky to be working with someone who has built such a model. And suppose data comes from the hospitals every week during flu season. How many flu cases are diagnosed? You could recalibrate the model with growing sets of data, and that's one possibility. And we'll talk about some other methods you could use, Markov chain Monte Carlo methods. But another possibility is to use some sort of recursive computation. In fact, that's what the Kalman filter will do. It will sort of have an estimate now that's sort of take into account the data in the model, and then when new data comes in, it will have updated that estimate and merged the two there. It doesn't have to go back and do entire recalibration of the model. Okay, and it turns out there's sequential Monte Carlo methods and particle filtering. So I'm going to have to go light on this, but the basic idea here is we have some system being studied. That's informed a state space transition model. Here we'll assume it's an ODE model, stop and flow model. And we're going to be doing some estimation from that, projection forward. And then alternatively, we're also going to be getting measurements over time. We're going to blend them using this gain matrix. And that's going to weigh sort of the measurements with the projections of this model. It's going to weigh each according to some level of error it associates with each. So if the model is judged as being really unstable, it's magnifying the uncertainty already present, increasingly we're going to weigh the measurements a little higher because less variable. On the other hand, if we're dealing with a situation where the measurements are really, really uncertain over time, maybe we're in areas with really large buildings that block the satellites, for example, satellite signals from reaching us, then we're going to be weighing the model more heavily. And based on that, we're going to get out what's called filtered estimation. This is called Kalman filtering, not because it blocks things, it's an ongoing process of sort of conditioning the data, in this case using the model. Okay. Now, there's some underlying Kalman filter projections. This is from a student of mine who's working on this for a project and probably as part of his thesis. But the classic formulation of this is something called Kalman filtering, okay? And this was created way back when. I think I have a picture of Kalman. No, I thought I had a picture of him here, but alas. His name is Robert Kalman. He's still alive. Created in the 1950s. And basically you have a set of ODEs. This is differentiation with respect to time, right? With some noise added to the system. And unfortunately, the Kalman filter, we have to make pretty strong assumptions about the nature of the noise. We assume it's Gaussian distributed. So it's white noise with a Gaussian distribution about at any however small amount of time we have, it's Gaussian distributed. And we're going to have some potentially measurable things, so that we're going to be able to compare to underlying observations. And fundamentally, when we have a measurement coming in, so we're going to be integrating forward these equations, and when we have a measurement coming in, we're going to be applying the best guess of what our measurement is, plus some gain matrix that says K here, which is going to be multiplied by the difference between our measured value and what we would have predicted our measured value to be based on our best guess of our current underlying state. So imagine a situation, we're doing this for a person walking, in an urban canyon in New York City. So we have some actual position X associated with them. And here we're going to be updating X based on our best guess as to how fast they're walking from an accelerometer or what have you. And we're going to take a difference between, for example, what the GPS satellite says it is at time t sub k, minus where we think they should be. Their location should be based on our understanding of the current speed and the updated location. And then we're going to essentially weight this. And this gain matrix will be essentially weighting the measurement and the model-based understanding of where we are. And we're going to adjust our estimate for the level of uncertainty associated with our current position. So not only are we keeping track of our understanding of the state space, what the current situation is, but our uncertainty about the state space as measured by this covariance matrix. And that too is a differential equation. So our level of uncertainty about the situation is evolving over time, and it will grow very quickly, for example, if we have a situation where our Jacobian here, our F, is in a situation of state space where a small difference in underlying state space, small bit of uncertainty leads to divergence in our estimates going forward. Imagine a situation where we're not sure at the initial time whether 2 people are infected or 10 people are infected, and it's in the early part of an outbreak. That's going to make a big difference, 3 days from now, how many people we think are infected, or 4 days from now. So we have this component here, and this Kalman filtering is very well canonicalized. It's used classically for planes, for missiles, for cars or vehicles. It probably is built into a lot of vehicles these days. It certainly is to cars, to missiles and aircraft over the years, and it's also built into those GPS devices as such in cars. What this particular student did, for example, with this, was to take data from an agent-based model where he knew the full situation. And it was quite a complex model. And he had an aggregate model, an SIR model. It was kind of a crude approximation to this. It oversimplified the situation. This had a network in it, and it may have had an evolving network. I don't think so. I think it was a static network, but it was quite involved. I think it had an exposed category, and this had no exposure, just SI and R, no exposure, no one who's infected but not yet infective. And so what was going on is that we had some synthetic ground truth, and then we had some measured data from this agent-based model to evaluate this Kalman filter. And we wanted to know how much could this crude model be corrected in this open loop, in this closed loop sort of way. If we constantly reground it with measured data, how good a job could it do projecting forward? So by itself, it's going to diverge from this. By itself, the SIR model, because it approximates so much about the underlying contact structure, because some of its parameters were even known to be off, it's going to be divergent from this. But if we have this measured data and we're constantly regrounding it in these measurements, maybe our projections forward are going to be pretty decent because it's regrounded. So on the basis of that, for example, he compared an open loop model, which is red here, The blue here, the thick blue line, is the actual underlying prevalence. The red model, you can see it's kind of off from it. It peaks early and it stays pronounced. And then these small, thin red and thin blue, for example, here are closed loop estimates, which continually reground the simulation model, which open loop is in red, thick red here. They continually reground it in the observed data and project forward from that. So in short, we could have a very crude model of a situation, which, as long as it's sort of refreshed with ongoing data, can be used reliably to project forward. So it's not just a matter of creating a model de novo, which is, just loaded with all sorts of accurate representation of the situation. We might be able to do pretty well with sort of a quick and dirty type of model, as long as we have data to support it. As long as we keep it grounded, we keep it honest by comparing it to data, and then we project forward for short periods of time. So that's an encouraging component. Any questions on that before I get on to the next example? So this is what's called predictor corrector method, okay? And it's a very powerful method. The next thing we're going to be talking about is posterior deprivation. So we've talked in this class about calibration. This is another candidate. 3 more lectures might get this. You can find this online. I have slides on this and a video on this where I record this for people totally new to it. So the idea here is it takes place many ways in the context of calibration. So we've talked about calibration in this course, trying to get a point estimate of the best parameter values. And in fact, your final problem set involves calibration, trying to arrive at the best parameter values that allow you to reproduce the underlying data. And some of the statistical methods we will use in goals of calibration will allow us to even estimate confidence intervals around point estimates. They allow us to estimate how uncertain are those point estimates. Problem is, there's a couple limitations here. One thing is we're assuming a single dynamic model. We're privileging one dynamic model. We're saying, assume this model, now get the best point estimate, and maybe get some variability around that. That's privileging the model. Often we have several hypotheses about what may be going on. We'd like to be able to consider several of them rather than together, rather than just independently when we ask what's the most likely parameter values. Second thing is that often we end up only with single point estimates, and they don't really make apparent, how these different point estimates lead uncertainty about those point estimates, lead to uncertainty in comparison, say, between interventions. Because some of them might flip, certain interventions being better than other. A greater than B with this point estimate, B greater than A with another one. If you have intervals around these estimates, you can't often go directly from those to intervals about those outputs, about the trade-off between interventions. And often even with estimate of intervals, you assume some sort of unimodal sort of situation, a single mode, and sometimes we end up assuming in calibration process a discrepancy function that imposes some pretty strong assumptions about the distribution of errors associated with the model. So within this context, we're going to be talking about a method which involves deducing what are called posteriors. So how many people here have seen Bayesian statistics before? Okay, just a couple. So I'm not going to be able to do justice to this, but the idea here is that the Bayesian framework provides us a way to reason about uncertainty in the context of observations, and how our uncertainty about a situation is updated on the basis of context. And here, crudely speaking, we have a prior distribution that describes sort of our level of uncertainty, the plausibility of different values, say, associated with our parameters. And this is called prior because we can formulate prior to observing any sort of data. It's based on our best guesses for what may be. And then based on observation of, say, emergent behavior, the sort of data we might have in calibration, we try to arrive at what's called posterior distribution. A distribution that incorporates that understanding of the data and the implications for the models that we're taking into account. And we take into account the likelihood that the model, given a certain set of parameter values, could explain the observed data. Okay. So the goal here is to move beyond point estimates in many ways. It's to give us a distribution over parameter values, maybe even over multiple models. That's not necessarily use model. We're not necessarily merely talking about the mode, the peak of it. And we can understand the overall structure of this. So here we're trying to arrive at a posterior distribution over parameter values. Probability distribution. Imagine two parameter values. It's going to give us a joint probability distribution. Tells us the relative probability of having any combination of those values. Now I'm glossing over the fact that in most cases it's a density, probability density of those values. But if they're discrete parameters, the probability of particular values. So then, given this posterior, we can then derive straightforwardly point estimates. We can derive likelihood. One intervention is greater than another. We can derive credibility intervals. We can derive distributions over model outputs of various sorts, etc. So we're going to a distribution, and I think I have a slide here. It'll be something like this with two parameters. And this is an example from one model that I was running recently. So here we have one parameter on the x-axis, one parameter on the y-axis, and we have probability distribution over these that peaks somewhere along this ridge here, and I think it's peaking up sort of at 0.039 on the x-axis, and somewhere up around 0.075 or something on the y-axis. It gives us a distribution. Now, Markov chain Monte Carlo techniques allow us to estimate these things. So basically, it's a principal way of generating samples according to a posterior distribution, and it's based conceptually on a Markov chain. Okay. So the overall idea here is that we assign a prior distribution. We formulate a likelihood formula in terms of simulation model output from one or more simulation models. And then we conceptually apply Bayes' rule to get a rule for the likelihood of parameter values in terms of data. So we have a rule here, a probabilistic rule, given this set of parameter values and the model output that follows from that, what's the likelihood that we'd have seen a given set of data? And then through Bayes' rule, we flip that around. We ask about what's the probability of having these parameters given this underlying data. And to do that, to sample from this, to sample from this posterior distribution, whose value we can formulate on the basis of a simulation model as well, we then generate samples. So here the simulation model, the dynamic simulation model, is used to arrive at this likelihood point. What's the likelihood that this set of parameter values would yield this sort of observed data? To understand that, we have to run the simulation model, for example, to ask maybe why concerns the number of people presenting for illness within a given week. And to estimate that, we have to run a simulation model with these parameters for, say, contact rate and for duration of infection. And we get a number of actual hypothesized infected people in that week. And we say, okay, given that number of actual infected people, what's the likelihood we see Y? What's the likelihood we see this actual number reported as infected? The simulation model is used in that process. So this is a statistical technique for generating samples from a distribution, but part and parcel of it, embedded within it, ladies and gentlemen, is a dynamic simulation model that's used to compute the posterior. And based on that, we can then sample from this distribution. So here we draw a candidate value within this, based on often a perturbation to a past one. using algorithms such as Metropolis or Metropolis Hastings. We then run the simulation model on this candidate value, and we use that to assess the likelihood we would have observed the observed value given that parameter, given what the model tells us results from that parameter. And then we can compute the posterior from that, like we did by multiplying times the prior. This gives us what's called a posterior. And then we accept or reject that candidate based on the ratio between the posterior there and our current posterior, or our most recent posterior. And it turns out this algorithm samples from a distribution. It samples from a distribution. And by sampling from that distribution, we can arrive at data like this. So we have this many counts for these different places. We're sampling from this distribution. We're getting a long list of samples that sample from this distribution. By plotting them out, we can see what the shape of the distribution is. Or we can run each of those samples through our simulation model to get various output for different outputs of the model, or to compare interventions and what have you. This is a very powerful technique for combining statistical simulation, in other words, an aspect of computational statistics on the one hand with dynamic simulation. Okay, so posterior derivation. Now, one thing I haven't talked about is there's a set of explicit modern Monte Carlo techniques that do what the Kalman filter did back here, but in a much more rich way. They have much less tight assumptions. These assumptions, which we had to impose to sort of arrive at estimates of the Kalman filter, can be vastly generalized using the sort of techniques we're using here with Markov chain Monte Carlo. So here we've been talking about linking dynamic simulation with statistical tools. Linking models and data was something I wanted to talk about, but maybe what I'll do is just load in a. I don't think you want to see the review from 371 again. So pardon me for just a second. I'm just going to load in some examples of the. Yeah, this is I love this quote. The quote from an epidemiologist: "Theory without data is myth, and data without theory is madness." If you don't have models to make sense of data, it's just a bunch of numbers, full sum theory, signifying nothing. And if you don't have data to back up your theory, you often go and spin off in ways that aren't really fully grounded. So we try to move in our work beyond myth and beyond madness. So we've created this Android-based system, and I just want to give you a sense of when I talk about big data. So we can measure contact networks on a multi-minute basis. People's distance from each other, for example, using Bluetooth strength. This is an example of some contacts. I think these were within our department. We've been running this all across North America in various places, but I think these particular ones were within our department. This shows different individuals in our department, staff, people like Merlin, people like professors and students and so on in 1 week, and then the same individuals in another week. And you can actually see, like, for example, here's person 4 here. Right now they're highly connected with 24, for example, and less so with 28, modestly with 38, and here in this other week, 37, 38 there's some, but it's modest, 13 is another big connection. These are people's evolution. We can do this every 5 minutes, every 2 minutes, depends on. So this is measure proximity, how close people are to each other. Yeah. So basically you have phones in discoverable mode. You can measure the strength of the signal, and the closer you are, well, from physics, the signal spreads out over time. It dies off in sort of a power loss sort of way, R squared, R cubed, and you can get some estimates of how far people are away together in terms of number of meters from signal strength. By me observing your signal strength. This is an app, and it puts out signals, hey, I'm here, periodically. And we listen for each other's signals. Contact duration, how long people are in contact. You notice anything odd about this graph? Can you say anything about this region of the graph here? So this is, in case you didn't notice, is a log-log graph. What would you say about this region up here? What does that remind you of? What other log-log graphs have you seen? This curve is characteristic of what sort of phenomenon? Power loss scale. Yeah. This is sort of scale-free sort of situation here for long periods of time here. So this is data collected by our phones. There's a couple other groups in the world working sort of at this level. One is in the UK, Cambridge University. There's another group at MIT. And it's amazing how well the data sometimes lines up. There's some drop-off out here, which may have as much to do with technology and as anything else. But we can measure contact duration way people can't. Accelerometry, this is the most impoverished of data, just showing data by hour. But we have, kind of hundreds of samples within a period of a few seconds, for example, for accelerometry. Geographic movement, you recognize our fair city there. People's movement around it, around Canada, for example. And that's movement from home to work. You can get a sense, okay, are people taking a bus, taking a car? And we have algorithms. How many people have seen hidden Markov models before? Is that familiar to anyone? Okay, a little bit. So we use hidden Markov models to classify some things. For example, someone indoor or outdoor. Is someone sitting or standing? Is the phone on their person or is it off their person? Maybe it's just sitting on a table, in which case it doesn't tell us a lot about them, the person. Or at least we can't be confident about what it tells us about the person, because we don't know how close they are nearby. But we can map out sort of movement patterns between people. Imagine getting this data, every 5 minutes for months. So we get something like commonly 1 to 2 million records per person per month out of a system like this. I think it's something like 40 megabytes a day, about those lines, because we get it across a whole bunch of different modalities. I think that's compressed. But so surveys that can be contextually triggered based on people's context to ask questions. And then we have a set of other systems that can be used with these devices. For example, a photo food diary, geocrowdsourcing, that's under showing success here. Custom sensors. So there's a team in engineering that's built a mosquito sensor, but actually it's a mosquito identification sensor too. It uses the wing beat frequencies of mosquitoes to identify what sort of mosquito it is. We've got a field test it this summer. There's an indoor positioning system to locate people within a building, because that's hard to do from GPS. It doesn't penetrate well. And so if you want to locate someone within the building, you can look for things that are fixed reference, like Wi-Fi signals, strength of Wi-Fi, the strength of Bluetooth. So the lab over here has tons of Bluetooth, all these Macs. But you have really strong Wi-Fi too, so you can localize people quite well indoors often, particularly on campus. TCP/IP communication monitoring, etc. And so we can map out things like activity level over geography. One unexpected thing is, in our participants, a lot of people get a fair bit of exercise in malls around campus, around the city. Here, Circle and 8, I think, out there. What resources are near people all through the day? What resources are they passing near, based on their actual activity spaces, not where they've reported being, or where it actually measures them as being. Social interactions at different times, for example, spaces in which contacts take place. This is university, I think, in here. Edmonton is, I think, up here somewhere. Some of the participants went up to Edmonton. These are various spaces as delineated by Wi-Fi nodes, which we detect. And the particular circles here measure sort of how many distinct participants and how many people that aren't part of the study, but we saw their smartphone somewhere nearby, so we know it's a particular person somewhere out there. How many people do you see in different places? This is a connectivity graph showing essentially if two nodes are connected, if we've measured participants moving from one location to the other within a 5-minute interval. So you can map out these sort of things, and then you can add in data from a whole whack of sensors that are now available. You can cross-cycle with weather to find out how people's activity patterns change based on weather, mapping Wi-Fi locations to GPS using tools like Skyhook, GIS databases to figure out, okay, crime statistics or park location services, etc. So give some notions of some of the things you can do with data, and models are needed to make sense of that. We are looking at, for example, we have a study which was just recently funded to look at gestational diabetics and their blood sugar levels over time in relation to physical activity, in relation to sedentary behavior, sitting and standing, in relation to eating, in relation to social connections, etc. There you might have a model within a person of glucose metabolism, and you have these various inputs affecting it, and you're trying to make sense of the observed patterns over time. So other issues, I mentioned performance. One thing is concurrency, another thing is model scaling. How does the performance scale with the size of the model, for example, the number of different types of behaviors or the number of different fields, etc. And we talked a little bit about the language impact and parallelizability. Time is running short here, so I thought I'd just mention a couple other frameworks. We've used AnyLogic in this course, in part because it's so flexible with multiple frameworks, in part because it is a leading framework for declarative modeling, etc. But there are others. For example, Repast is perhaps the #1 framework out there. Recursive Forest Agent Toolkit, can't remember the agent simulation toolkit, I think. And this is an open source system for doing agent-based modeling. It's very, very powerful. It's also based on Java. It's not the only one. NetLogo is a beginning system that uses the logo language. Some of you may have used when you were younger. And it simulates agents in more stylized situations often. There's others as well. The Swarm Toolkit, for example, Mason. Yes, that's right. That book uses NetLogo. That's exactly right. Yeah. Unfortunately, NetLogo lacks facilities, for example, for calibration and I think automated sensitivity analysis. So it's to the degree we want to cover those in class, it's not the best toolkit for it. So others, well, we've seen Vensim. There's other toolkits for that. Berkeley Madonna is a popular one. PowerSim, I think, Insight Maker, etc. Books. Okay, so Alex had mentioned some books. There's a variety of interesting contributions. This gives just a glimpse of some. One is the book that I recommended for the class. One of the two books. Another is a book by Josh Epstein called Computational Social Science. It's more of a kind of collection of successful projects within the use of agent-based modeling that are very thought-provoking, very provocative in some cases, and interesting, worthwhile. I believe that's within the past few years that was contributed. Networks. So Mark Newman, I think he's the author for Structured Dynamics of Networks, which is a collection of scholarly papers on networks. On the flip side of the spectrum, this is a set of popular books like Steve Strogatz's Sync, which is a wonderful book I'd recommend to people. A little bit more popularized, but he's much more popularized than Mark Newman. Maybe more popular than people in the class would always like, but it has some great stuff in it, some very compelling sort of ideas, including some topics we didn't talk about, like entrainment, ways in which the dynamics, once you have people connected, the ways in which the dynamics become interlinked. So he talks about, for example, fireflies and the blinking of fireflies in sync, which I've seen in Malaysia. It's amazing because you see, fireflies over a wide area and they're blinking in sync with each other in this way that is remarkable, or crickets chirping and singing and so on. These are phenomena that combine dynamics with network considerations, and he talks about some of this. Barabazi has a book called Linked that also tries to sort of communicate some of these ideas more broadly. And Watts has a book called Small Worlds, which are interesting. Tom Valente has Social Networks and Health, which is quite focused on the health area, but is also an interesting book. System Dynamics, Moorcroft has some interesting work. Sturman's Business Dynamics was recommended. And there's a book by Ford called Modeling the Environment, which is kind of interesting. It's a set of conferences and so on, which are in these areas, and contributed content here. So I think those are all the comments I have within this wrap up. I sincerely regret I couldn't focus more of these things in here, but I think we've done an okay job covering the material. Are there any questions that I can answer right now from students here? Yeah.
I think you're going to talk about how where simulation is fun.
Yeah.
Simulation is fun in the future.
Sure, I could do that. I mean, I think these are many of the most important things here. At a broad level, what we're seeing is dynamic simulation of the sort we're using here. It's being viewed increasingly as less of a novelty and more of an essential for effective decision making with respect to complex choices. And this was first pioneered in certain areas where the need was extremely clear from the last century. That includes some areas of business. Marketing, for example, is one of them. But there's other areas like infectious disease where it was recognized early on as being essential. Increasingly, though, what you're seeing is it penetrated to address very, very different areas. And simulation, it's hard to express accurately what's going on by just using the term simulation, because each of the sorts of simulation we're talking about in this class are used in different sub-communities with different interests and goals and questions in mind. So discrete event simulation, for example, is used a tremendous amount with efficiency issues. How do you run an efficient operation? How do you locate resources where they're needed, or assess the advantages to throughput, how quickly you can service things by marshaling resources. Agent-based modeling is used tremendously within the sphere of interpersonal communication and representing agents with rich sort of representations of what's going on. So modeling driving behavior, for example. System dynamic simulation is used a lot with stakeholders when you need to capture stakeholder qualitative understanding and speak to them. Often it uses simpler formalisms. But I think one of the big trends we're seeing beyond what I've talked about here, linking up with data, is the situation that AnyLogic presages, which is bringing together the multiple sorts of modeling. So this is not going to be about one project using either this or that, which is largely bad. But it's not only that, it's like almost one subfield predominantly using one or the other right now. And increasingly what we're seeing is particular modelers using a suite of models to investigate an issue, but increasingly yet using combinations within a given model, having components within different frameworks. So for example, I spoke earlier about having within a given model state charts and maybe agents connected in networks or arranged in space, but with stocks and flows driving some of their dynamics. A classic example of this would be body weight change over time in response to physical activity, in response to eating. People are starting to use models like this, including in my group, including at Brookings Institution in the US. Another example would be metabolic models blood glucose metabolism for diabetics, so that you can project forward for these diabetics if they're going to enter a dangerous region, and alerting people to this whole real-time predictive simulation. I think this, we're not going to see models and data as solitudes, or models where they're initialized to data, where they're parameterized to data up front, maybe calibrated, and then they're set loose, and they're just used and on. We're going to see models as sort of a living, breathing things which get data in, and which are constantly sort of repositioning their stance with respect to what's going on, informed not only from prediction, but by arriving data. And we're also going to see evolution towards, I should have put this in here, it's another area we've contributed, towards systems which try to help manage the complexity of the modeling process. Because the modeling process, like the software development process more generally, has a huge amount of complexity associated with it. I mean, you've gotten probably some sense of this from your problem sets, your project. You know, you have this model, you do some experiments with it, you see some output. Unless you're careful and take these things down, it's easy to forget what gave you what at what time. And you find yourself having to go back and rerun it, or you find yourself wondering, when I saw that really interesting result, what earlier version of the model was it? And you have to go through several earlier versions. And so we're seeing some steps towards something that we've done some pretty good work prototyping, but which industry isn't yet fully adopted, which is hasn't really adopted yet in much at all, which is essentially like modeling notebooks for, they're almost like lab notebooks for modeling, so that you have all complete records of the experiments you've run, what the assumptions were, what particular version of the model it was with, what the parameter values were, what the output was, what was the result of the analysis on that output, where did the data for the parameter values come from, you know, what were their original sources, what was the provenance, the level of confidence about that. And you're going to see models sort of couched within this broader context. Just as in software, we've devised tools like Subversion or Git for software project management, continuous integration systems like Jenkins, or like Cruise Control for maintaining software in a way that automatically reruns it when people check in. You can have distributed teams and so on. That's not really present for modeling right now. Modeling is kind of, the support for it infrastructurally is in its infancy. And a lot of it is done kind of ad hoc. And what you get is sort of horror stories where people have to reproduce an early result and they end up spending a week trying to locate, you know, where that came from, or they go, over time working on their models, and they find thousands of files output, and they don't know which are needed and which are not needed, because, you know, some of them may still be needed because of notes elsewhere in a document of some sort which exists with no referential integrity to those things. So in other words, they're afraid to delete everything. They're afraid to delete old versions of models that they think are buggy because something may depend on them. And so there's no real adequate support. And I think modeling is reaching a level of maturity where you're going to see more and more of that. Another thing is support for that infrastructure. Another thing you're going to see is a emergence of platforms that really make modeling much easier to accomplish for those not trained in computer science or engineering. So sort of Vensim-like things for agent-based modeling. But one of the biggest gaps in this area, I have to say, folks, is the training side. I'm routinely approached by people who want to do projects, and I just, there's not enough training going on to graduate the people who are needed to deliver on these projects. And what I see now is an imbalance between demand and supply of needs to do this sort of work and availability of human resources. And what's needed most of all, I think, is frankly people like you. It's people who are well-trained technically, who aren't afraid of getting into the mathematics to double check conclusions, are comfortable with doing statistical analysis and outputs of models, and who are able and willing to work with the code base where necessary. This is really what's needed to sort of allow it to take off. I think in many ways it's a supply limited phenomenon, and people have sort of realized, okay, we need these tools. The problem is, compared to statisticians, you can go hire statisticians dime a dozen. They're actually not cheap, but it's not dime a dozen, I shouldn't say. They're not cheap, yeah, right. They're not cheap, but they are widely available. They're routine commodities. I don't want to commoditize these, but there needs to be training opportunities in place additionally for people in the dynamic modeling area, because that's where the bottleneck is right now. And so there's a lot of people who want to do applications of this work. There's people who want to use these models, but they need to partner with someone who's savvy. They can't do it by themselves. You take your average health scientist, really interested in agent-based modeling, and you pair them with any logic, and they see the potential, but they can't fully act on it. They need someone to work with from the computational side that will help them. So there's huge opportunities there. I think over time it'll get easier for the health scientists, but there's still going to be a need for people to be real virtuosos on the technical side, and can customize pieces of a model. What it will allow folks like you to do over the long term is do less and less routine stuff in the models and more of the cream. Deal with the sort of the most interesting, distinctive components of the models. So you look at the evolution of software development over the years. Back when I was a young man, there's a lot of work still done in assembly language, for example. One of my first pieces of commercial software, I remember writing routines to update the screen in assembly language and so on, because you needed it for performance. These days you can just ride atop a huge amount of infrastructure. You want regular expression parsing, you don't have to go out and write your own regular expression parser. You could go get one. You wanna create a you wanna simulate ODEs in your application. You could use something like ODE to Java created by researchers here. You want to do work with rich graphics. There's ways to do that more easily writing atop OpenGL or other libraries rather than writing your own. So increasingly we have software engineers who have been leveraged to allow us to do to focus on the more challenging components of a problem and to build bigger systems. Modeling is going in that direction. The models are becoming richer, bigger, and they're increasingly well supported by software and by tools. In the medium term, what this is going to mean is, you're going to be able to, instead of writing the code manually, to do something like implement state charts. You can write atop of that abstraction, saying that if you wish to. You can write atop the abstraction of events, and you can focus more on sort of the underlying logic that is trickier. So we're moving as a field to a leveraged place where we can actually focus more on contributing, unique components of it that can't be easily automated. But again, it is supply limited. There are very, very few people who combine rich underpinnings and technical side with an appreciation, ability to communicate with people on the application side, and are working in this area. So, simulation modeling, I think it has a huge set of opportunities. I think these opportunities written large here have on the screen, have a lot to do with many of the possibilities with it, because we're going to be doing this work in our data-rich area increasingly, and with the analytic tools to allow us to make sense of that data. So those are just some comments on directions for the modeling field. I'd love to, share comments one-on-one with people if there's more interest in that. So, it's been my great privilege in this class to be able to include all of you on it. I know there's a lot of work still to be done. Got to get you the problem sets and the pop quizzes back. We need to finish up projects for those actively working on them, and we need to have something called the final exam. I will be holding a review for the final exam prior to it. I may be holding two. I'm trying to schedule that right now. My guess is that it will be, for your sake as much as for mine, a couple days before the actual final takes place. But before, before the very end of the week, where there was some discussion of an early final for one of the students. So we'll try to make sure that everyone can come to it. I will put out a doodle poll so that you folks can indicate your availability, and we'll see if we can pin down the date. I'll probably have it be a two-hour component, and we can take it however you want. It'll be your chance to ask me whatever questions on the material, and for me to answer. But right now, the final's not yet a speck in the cosmic eye. I've got some ideas about what will be on it, but I can't speak with authority yet. Okay? So please come and talk with me. I'd welcome anyone here, and I will try to have lots of office hours between now and the end of the month. Again, great privilege. Appreciate your bearing with the difficulties of getting a course unmoribunded, and importantly, with scheduling this course in the first place. That bounced all over the place, and I appreciate your patience with that. And hope to see you in some future courses, but in any case, in the next few weeks. Thanks.